Okay, so I'm going to start with today's lecture, which is to continue our discussion that we were having last time. Let me remind you briefly what we were trying to do last time. What we were trying to do was basically we were trying to characterize the wireless channel. So we were basically characterizing the wireless channel. So if I were to briefly recap, so really characterizing the wireless communication channel, and what we said is the following thing, that is when I have a wireless communication system, let's say this is a base station and I have a mobile station, right? So when I have a wireless communication system, wireless link between a base station and a mobile station, so this is my base station and this is my mobile station, right? And in addition to the line of sight path between the base and the mobile station, I might also have several excuse me, sorry, several non-line of paths. For instance, these are reflected by these different objects in the propagation path, right? So these are the non-line of sight paths, right? And therefore what I have is a multipath channel with impulse response which can be modeled as H summation I equal to 0 to L minus 1 AI delta P minus tau I. So this is these are the different AIs are basically, these are the amplitudes of the multipath component and tau I are the delays, right? So AI, these are the amplitudes and tau I, these are the delays. So what we said is the following, that we basically do not have a single path but we have a multiple path. So the signal is arriving via multiple paths, right, starting at tau 0, tau 1, tau 2, so on up to tau L minus 1, right. So the first component arrives at tau 0, the last component arrives at tau 1, and there are several components that arrive in between. So the signal is arriving over a spread of time, right. So there is not a single time instant where the signal is arriving at. The signal is arriving at several time instants which are spread over time, right. And that spread is nothing but the delay spread. So if I plot the channel impulse response, the channel impulse response looks as follows. That is basically, there is a path, there is an impulse at a naught at time tau naught, there is an impulse at tau 1 of a1, a2 at tau 2, so on. There is al minus 1 at tau L minus 1. Alright, so the first component is arriving at tau 0 and the last component is arriving at tau L minus 1. So these various components are arriving over a spread of time. These are arriving over a spread of time, and this spread is known as the delay spread. So that this spread, this time interval over which the various components are arriving, this time interval is termed as delay spread. Right? Delay spread is basically there is a time interval over which these various components are arriving. Right? This time interval over which the different components, this finite time interval over which the different components are arriving, this is termed as the delay spread. Also, if everyone might remember, I don't know how many people remember from last lecture, we said in a typical outdoor channel, this is the reason that this is the logic that we use in a typical outdoor channel. If I look at a typical outdoor channel, right, the cellular radius, these are the radius of cellular systems, these are approximately of the kilometers, right? The cellular is in a cell, the cell radius is approximately order of kilometers. Therefore, the differences and the differences, let's say this is a direct path of some kilometers and this is an indirect path of some kilometers. Therefore, the distances and the differences between the distances are approximately of the order of kilometers. So, the distances are roughly of the order of kilometers, right? So, the distances are roughly of the order of kilometers. If the distances are roughly of the order of the kilometers, what can we say about the delay spread? That is, if d1 and d2, the two distances involved in this are roughly of the order of kilometers, that is when I am looking at d1 and d2, and d1 minus d2 also approximate of the order of, let's say, 1 kilometer. What is the delay spread? What is the order of the delay spread? Can someone calculate and tell me what is the delay spread if the distances are roughly of the order of kilometers? What is the order of the delay spread? We calculated this last time. Does anyone remember? What is the order of the delay spread? Does anyone remember from our calculations last time? In microseconds, correct? How do we get that number in microseconds, correct? I think yeah, please tell me, how do you calculate the delay spread? The answer is correct, it is microseconds. How do we get that? How do we get that result? Can someone tell me how we get that result? Yeah, the answer is basically the difference in distance d2 minus d1 or d1 minus d2 divided by c, velocity of ride, right? Because the velocity of the wave is c, velocity equals v into 10 to the power of 8 meters per second. Delay spread right, because delay spread, because propagation corresponding to d1 is d1 by c, propagation corresponding to d2 is d2 by c, right? Therefore, the delay spread, that is the time interval between the first and last components, is d2 minus d1 divided by c, which is equal to 1 kilometer divided by 3 into 10 to the power of 8, approximately basically 3.33 microseconds. And of course, this is not the exact delay spread. What I'm not saying that basically this is the exact delay spread. I'm simply saying roughly, approximately the delay spreads are of the order of microseconds. So what this says is basically the way to interpret this result is not is not in the sense that the delay spread in every cellular system in every cell is 3.3 microseconds, but what it is saying is since the distances are roughly of the order of kilometers, the delay spreads are roughly of the order of microseconds. So delay spreads, so cellular delay spreads cellular delay spreads are roughly of the order of microsecond. The other thing that I wanted to point out was the other thing I wanted to point out. The other thing that I wanted to point out was uh, how to measure this delay spread. How to measure how to measure this delay spread. And we said one simple way to measure the delay spread is the following thing, without considering anything. If everyone remembers, we said the first arriving component is tau naught, the last arriving component is tau L minus 1. Therefore, one can say the delay spread is simply tau L minus 1 minus tau naught, which is equal to, we can call it as tau max, which is the maximum delay spread. So one way of measuring the delay spread is, so if I were to go ahead, one measure of delay spread is, okay, hang on, there is some request saying that voice is not clear. I've increased the voice of the speaker volume. Can you hear me? No, it's not a problem with me. Is that okay? Can everyone hear me? Okay. So one measure of the delay spread, one measure of spread is basically simply say equals tau L minus 1 minus tau 0, and this is known as tau max, which is the maximum delay spread. This is also known as tau max, which is the maximum delay spread. This is the So basically what we are saying is look at the first arriving component, look at the last arriving component, and the differences between this is basically what is the first arriving component, what is the last arriving component. The time interval between them is basically the delay spread. That is what we are saying. Okay. So the time interval between the first arriving component and the last arriving component is the delay spread. But this is a very simplistic view of the delay spread. For instance, let's say first arriving component is arriving at 1 microsecond, last component is arriving at 5 microseconds. Delay spread is 5 minus 1, that is 4 microseconds, right? Something like that. But this is a very simplistic and fairly inaccurate also with respect to analyzing the delay spread. Can someone tell me why is this not a very accurate measure? That is simply taking the difference between the first and last arriving components. Why is this not an accurate reflection of the delay spread? Can someone tell me, answer this question? Simply, if I take the difference between tau L minus 1 minus tau naught, why is this not an accurate characterization of the delay spread? Yeah, we are not considering the delay and power levels, and moreover we are not considering the gains of the different paths, right? Because for instance, let's say we have a profile with some strong paths and then some weak paths. These weak paths might unfairly distort the delay spread, right? Because these are the strong paths, but these paths are very weak compared to those strong paths. It's unfair to say that the delay is simply the difference between the first and the last components, because these paths are weak in power. The last arriving paths are the paths that frequently arrive after a large amount of delay. Typically the paths which arrive after a large amount of delay are fairly weak, right? Because the paths, the strongest paths are the ones that are corresponding to the, and also the scatterers which are close by. As the distance increases and the delay increases, the signal strength also, and also because of the long distance the signal has to travel, the signal strength also decreases considerably, right? So the last arriving paths, or the paths that arrive later, are frequently very low in power unless there is no line of sight component. In some scenarios also very legitimate, like in a dense urban environment where there is a dense clutter and there are dense obstacles such as buildings in the path of propagation, where the line of sight path is attenuated, or frequently there is not line of sight path also. In those scenarios, of course, the non line of sight paths also have a significant power. All right, so it's basically a give and take. All right, it depends on the scenario. Okay, so what I'm saying is basically it is simply taking the difference of time between the first and last arriving path is not a good measure, or does not reflect the true delay spread, because we are not weighing the delay by the power in the path. What is more important is basically not just a delay, but what is the amount of power, or what is the fraction of the power in the wireless communication signal that is arriving at that delay. And for that purpose, we said we are going to use the following. Uh, Given this profile delta t minus tau I summation I equal to 0 to L minus 1, I said I'm going to create a power profile. And the power profile is as follows: I equal to 0 to L minus 1, magnitude AI square. This is not an impulse response, by the way. This is simply a power profile. This is magnitude AI square. This is the power at delay. And we said we can also denote this magnitude AI square by GI. So I am denoting GI equals magnitude AI square. Is that clear to everyone? So I am creating a power profile. I hope everyone can see this thing. What I am doing now is I am creating a power profile. Fine, everyone can see that I am creating a power profile. Fine. What is the power profile? Power profile simply tells me what is the power that is arriving at what delay. For instance, here I have power magnitude AI square, which I am denoting by GI, arriving at delta at tau. So GI, this is the power, tau I, this is the delay. So if I basically plot the power profile looks something like this. Power G naught at delay tau naught, power G1 at delay tau 1, so on, power GL minus 1 at delay tau L minus 1. Okay. Now what I am going to do is basically I am going to put these coefficients BI. What is the coefficient BI? BI is basically fraction of power in the BI is the fraction of power in the ith path. Does anyone remember what is the definition of BI? Any student, does anyone remember what is the definition of BI? What is the fraction of power in the ith path? Bi equals Gi by G naught, correct. G naught plus G1 plus G L minus 1. This is Bi. Bi equals Gi divided by sum. That is basically, if you look at it, power in ith path divided by total power, that is nothing but Gi divided by G naught plus G1 plus GL minus G naught plus G1 plus so on up to GL minus 1. That is the fraction of the power in the ith path. Alright, so the fraction of power in the ith path Bi is Gi divided by some Gi. Now I can compute the mean delay. Now of course the other important property is if we add B naught plus B1 plus BL minus 1, that is equal to, can someone tell me what is this equal to? That is obvious, that is equal to 1, because if I add all the fractions, the sum of all fractions has to be equal to 1. Further, each fraction is also equal to 0. Observe that Bi is greater than or equal to 0. Each Bi is greater than or equal to 0. Therefore, mean delay is basically now simply combine each delay in proportion to the fraction of power. Mean delay tau bar equals B naught T naught plus B1 T1 plus BL minus 1 tau L minus 1. Right, this is also what we are calling as the remember, this is also what we are calling as the mean delay. So each delay I am weighing it by the fraction of power, B naught by T naught, B1 by T1, so on, BL minus 1 by TL minus. So basically summation of delay times fraction of power. Right? It is natural. Alright, it makes sense, intuitive sense, because I'm weighing. I'm saying it's meaningful because now I'm simply not considering just the delay, but I'm weighing the delay by the fraction of the power. Alright, makes sense. Which is also nothing but summation Bi tau I, and remember each Bi is Gi by summation Gi, so this is nothing but right. Basically tau bar equals summation Gi tau I by Gi. Is this clear to everyone? Everyone able to understand this? I bar tau bar, which is the mean delay, that is the roughly the mean delay. What is the mean delay of the signal? If someone were to ask, see, there is a delay spread, right? So there are many components which are arriving at various delays. So if someone were to ask you, what is the mean delay of the signal? What is the average delay at which the signal is arriving? You have to give them one answer. Then what is the sensible answer that you will give him? You cannot simply say take the average of the first and last. You cannot simply take tau naught plus tau L minus 1 by 2, right? Because that is not meaningful, because some paths have more power, some paths have less power. So the meaningful thing to do is to basically average the delays, compute the weighted average corresponding to the power in each component. Okay, fine. Because some components have very low power. So this way we're automatically rejecting the components which have very low power. Alright, fine. Okay. Now therefore what is the delay spread? Now what is the delay spread? Now delay spread naturally, once I compute the mean delay spread equals deviation from the mean. Delay spread equals the deviation from the mean. Therefore, deviation from the mean for each delay tau I is nothing but tau I minus tau I bar square, right, times Bi, which is the fraction of power, summation I equal to 0 to L minus square root. Now, let me repeat again what is this. Look at this. Tau I minus tau bar is basically the deviation. I'm taking the square of this, right? This is the square of the deviation. Tau I minus tau I bar. Alright, this is the square of deviation. What is Bi? Bi is the fraction of power. I'm performing summation I equal to 0 to L minus 1, and then I'm taking the square root. Fine, this is nothing but the standard deviation. Everyone can remember this is nothing but the standard deviation. This is the value minus mean. This is the mean whole square multiplied by the probability or multiplied by the fraction, summation I equal to 0 to L minus 1 under square root. This is nothing. If everyone remembers, I hope is familiar with the definition of standard deviation. This is the standard deviation. Alright, this is a standard deviation with respect to the mean delay. This is also known as the root mean square. This is the root mean squared delay spread. Alright, this is the root mean squared delay spread. Alright, everyone get the point? So this is the root mean delay spread. This is the standard deviation. This is also known as, in wireless communication, this is also known as tau RMS. Tau RMS basically stands for, RMS means root mean squared, because we are taking the square, we are taking the mean by weighing by the fraction, and we are taking the square root. So this is also the root mean squared delay spread. So this is another way to characterize the root mean squared delay spread, is another way to characterize the delay spread of the system. This is the root mean squared delay spread. This is basically another way to characterize the root mean squared delay spread. This is another way to characterize the delay spread. This is another way to characterize the delay spread. This is the root mean squared delay spread. Everyone get the point? Alright, fine. Okay, everyone able to understand what I'm saying? So this is another, a more realistic and a more practical way to characterize the delay spread. A more realistic and a more practical way to characterize the delay spread is the root mean squared delay spread. Also, now you can write this by substituting for Bi in terms of the Gi. You can also write this as, each Bi is Gi by summation Gi. Therefore, this is I equal to 0 to L minus 1 Gi tau I minus tau bar square this is in terms of the GIs. This is basically the, this is in terms of the, this is in terms of the different GIs, right? So this is GI divide GI tau I minus tau bar square summation divided by summation of GI divided by summation of GI. Okay. Alright, is that clear to everyone? So this is Gi tau I minus tau bar square divided by summation of Gi. Okay. Is this clear to everyone? Everyone able to understand what is happening so far? Any questions so far? If you have any questions, let me know at this point. If you have any questions, let me know. All colleges, if you have any questions, please let me know at this point. Anyone having any questions? Is it clear to everyone how we are calculating the root mean square delay spread? Is it clear to everyone how we are calculating the root mean square delay spread? Okay, then let us now do a simple. Practically, will there be only one LOS path? Yes, there is only one line of sight. Line of sight by definition means the point joining. Practically, will there be only one line of sight path? Yes, in practical systems there is only finite number of non-line of sight paths, because infinite number of non-line of sight paths means basically the signal has to keep coming on for infinite duration. That is not possible, right? So there are only a finite paths. Practically there are only a finite number of non-line of sight paths, and there is only one line of sight path. That is what I am saying. Practically there are only finite number of non-line of sight paths, because there are finite number of scatterers. Because there are finite number of scatterers, there are only finite number of non-line of sight paths. Any other questions? Any other questions? Let us proceed with a simple example. Let me consider this scenario, try to compute the delays. For instance, let's say I have the following power profile at tau naught equal to 0 microseconds. I have signal of minus 20 dB. What about the other path signals like scattered, diffracted path? That is what I'm saying. I'm not sure what the question is. Scattered paths, diffracted paths, they are exactly the non-line of sight paths. And what we are saying is there are a finite number of scatter. Non-line of sight means basically scattered and diffracted paths, because these are precisely the non-line of sight components, which are the scatters and diffractors in the path of the signal. And because there are finite number of such objects, the number of non-line of sight components is also finite in practical scenarios. That is what we are saying. I hope that clarifies. Okay, so is that correct? Is that clarifying? GIT is asking a question. What about the scatterers? Scatterers are precisely the non-line of sight paths. Is that okay? Okay. So tau is 20 dB and tau naught equal to 0 and minus 20 dB at 0 microseconds, and I have minus 10 dB at 1 microsecond, and then I have 0 dB. These are the powers I am writing. 0 dB at 3 microsecond, and then further again I have minus 10 dB at 5 microsecond. So now if I write this down as a table, let me just write down my power profile and then you will see tau naught equal to 0 microsecond, G naught equals minus 20 dB, at tau 1 equals, in real time how to find the value of L, which is the number of non-Lando cycles. I will come to that, please. I am going through the example after this thing. T naught equal to 0 microseconds, T1 is equal to tau 1 is equal to 1 microsecond, G1 equals minus 10 dB, tau 2 equals 3 microsecond, G2 equals 0 dB and tau 3 equals 5 microseconds and G3 equals 10 dB. Okay. So my channel profile is as follows. My power profile is as follows. Tau 0 is equal to, the delay 0 is 0 microseconds. I have G naught is equal to minus 20 dB. Tau 1 is equal to 1 microsecond. At 1 microsecond I have a path of gain minus 10 dB. At tau 2 equals 3 microseconds I have a path of gain 0 dB. At tau 3 is equal to 5 microseconds I have a path of gain minus 10 dB. Okay, fine. Now can someone tell me what are the corresponding linear values? Minus 20 dB is equal to, which means what is the linear value? Can someone tell me corresponding to minus 20 dB what is the power corresponding to minus 20 dB? To minus 20 dB what is the power? Can someone tell me corresponding to minus 20 dB what is the power corresponding to minus 20 dB? Let me write the question over here. Minus 20 dB. What is the power corresponding to minus 20 dB? Minus 20 dB equals 0.01, correct. Minus 20 dB because 10 log 10 power is equal to minus 20 dB, which means minus 20 dB equals 0.01. Minus 10 dB, what about minus 10 dB? Minus 10 dB equals 0.1. 0 dB equals 1, correct, and minus 10 dB equals 0. Okay, very good. So G naught is equal to, in linear scale, that is not dB scale, G naught is equal to 0.01, G1 is equal to 0.1, G2 is equal to 1, G3 is equal to 0.1. Okay, fine. Now therefore, GI, we said mean delay equals summation GI TI by summation of GI. This is the mean delay which is tau bar. Mean delay tau bar is equal to summation GI TI divided by summation of GI. Now can someone tell me in this case what is the value of L? How many multipath components do we have? Can someone tell me what is the value of L? L equal to 4, that is correct. L is equal to 4. The number of multipath components L is equal to 4. Therefore, this is equal to summation G0 tau naught plus G1 into tau 1 plus G2 into tau 2 plus G3 into tau 3 divided by G0 plus G2 plus E is equal to which is equal to this is G0 into tau naught plus G1 into tau 1 plus G2 into tau 2 plus G3 into tau 3 divided by G0 plus G1 plus G2 plus G3 which is equal to this is equal to 0.01 into 0 plus 0.1 into 1 plus G2 into tau 2 1 into 3 plus 0.1 into 5 divided by 0.01 plus 0.1 plus 1 plus 0.1. Someone tell me, someone calculated and tell me PSG that's good, correct, 2.97. Can someone else also calculate? Can anyone, can some other college also please calculate and tell me the value? Please perform this calculation, that is summation GITI divided by summation of GI. What is the mean delay tau bar? Mean delay tau bar. What is the mean delay tau bar? Well, it is not clear which corresponds to line of, not said which corresponds to the line of sight. We have not said which corresponds to the line of sight path. Simply we are saying this is the power profile. It does not matter which is the line of sight path, which is the non-line of sight path. I hope that answers the question. That is 2.97 micro. Okay, so this is 2.97 microseconds. Fine. That is the mean delay. Now what do I have to do basically to compute the RMS delay spread? Therefore RMS delay spread is equal to summation of E naught into tau naught minus tau bar square plus G1 into tau 1 minus tau bar square plus G2 into tau 1 minus tau bar square plus G3 into tau 1 G2 into tau 2 minus tau bar square plus G3 into tau 3 minus tau bar square divided by G0 plus G1 plus G2 G2 plus G3, that is equal to square root of point 0.01 into tau naught is 0 minus 2.97 square plus 0.1 into 1 minus 2.97 square plus 1 into 3 minus 2.97 square plus 0.1 into 5 minus 2.97 square divided by 1 plus 0.1 plus 1 plus 0.1. Hopefully this is clear. What I'm writing here is G naught tau naught minus tau bar square, Gi tau I minus tau bar square summation divided by summation Gi whole under root. And therefore what is this value? 0.86 microseconds, that is one column. Can someone else also calculate this value? Tell me what is the answer that they are seeing? In some colleges, can you? What is the significance of delay spread in wireless communication? The delay spread in wireless communication, we'll come to that. We'll come to that. In the future lectures, we'll talk about what is the impact of delay spread in wireless communication. Yes, we'll come to that. That is a good question. That is an interesting question. We'll come to that. Can any college please also calculate this value? Can any other college please calculate this value? Yeah, 0.85 microseconds. Correct. That is the correct answer. Approximately 0.85, 0.86 microseconds. So approximately 0.86 microseconds. Yeah, correct. B0 is 0.1. Correct. Got it. Thank you. So this is 0.86 microseconds, approximately 0.86 microseconds. So tau RMS is approximately, the value of tau RMS is RMS delay spread equals 0.86 microseconds. And you can see we clearly get a very different value compared to the max delay spread. What is the max delay spread? Max delay spread tau max from this equals tau L minus 1 minus tau naught, which is L tau 3 minus tau naught. What is max delay spread? Max delay spread is 5 microseconds, right? You can clearly see maximum delay spread is 5 microseconds. But when we weigh it by the power, when we are weighing the delay by the corresponding power, it clearly reduces to something much smaller, that is 0.8. And also you can see here, if you look at this, basically the mean delay is 2.97 microseconds. That is some very interesting, because it says strongest path is at 3 microseconds. So the mean delay is corresponding to the strongest path. What it's saying is the rest of the paths are significantly lower, 10 dB and 20 dB lower than the strongest path. This is the strongest path, and the other paths are 10 dB and 20 dB lower than the strongest paths, and the mean delay is 2.97, which is approximately 3 microseconds. So this is what we by weighing by the fraction of power. So if there are any quick questions, I'll take it. I think there was one question relating to what is the significance of delay spread on wireless communications. That we will come to slightly later. That is in the next next lecture, subsequent lecture we will come to. Can we always say that? Can we always say what? It is not clear. Can we say what? What is the excess delay and what is the significance? This is what we will come to. That is the delay spread. What is the significance of the delay spread that is what I will come to in the upcoming lectures. I think that is the issue that we will come to in the upcoming lectures. Can we always say that? Can we always say what? That is not clear. 0 less than RMS delay spread, less than mean delay spread, less than max delay spread. You think about it. It's an interesting question. What is the relation between the RMS delay spread and the max delay spread? And also, can the RMS delay spread be less than 0? Can the RMS delay spread be less than 0? Anyone can say, can the RMS delay spread be less than 0? And can the RMS delay spread be less than the max delay spread? RMS delay spread cannot be less than 0 because RMS delay spread is the sum of positive quantities. If you look at this, RMS delay spread is basically the sum of positive quantities, tau I minus tau bar square Bi, right? So RMS delay spread is always greater than 0. Can RMS delay spread be greater than the maximum delay spread? Can someone answer? Can RMS delay spread be greater than the maximum delay spread? Who can tell me the answer? Yes, that is the correct answer. RMS delay spread cannot be greater than the maximum delay spread. Why is that? Can someone justify it? Why is that? Well, square root will give a negative value, but can standard deviation be negative? Does it make sense to consider a negative value for delay spread? What does it mean to say that the delay spread is negative? Delay spread is a time interval, right? What does it mean to say that the delay spread is negative? Is it logical to consider the negative of the square root? Yes, correct. Because you are taking the weight of the several fractional weights of the several components that will always lie between the maximum and the minimum, right? Because go back here, what is the delay spread? Delay spread is nothing but it is Bi tau I minus tau bar square, right? The minimum of this will be 0 and the maximum quantity of this will be tau max. So if you are taking a fractional weighting of these different spreads, it has to always lie between 0 and tau max, right? Consider this. If you go back to this plot, basically what are you doing? You are taking simply the fractional weight. You are weighing by the fractional power each delay from the mean. The minimum value of this is 0 and the maximum value of this differential, the maximum can be tau max. Therefore it has to be because of the weighted power. That is correct. Because of the presence of the weighted components. That is also correct. Logically delay has to be it is a time delay. Therefore it is only the positive square root. Any standard deviation is a positive quantity because delay is logically it is only a positive quantity. There is no sense in basically a negative delay spread. That does not make any sense. The delay is only positive. It is either 0 if there is only a single path. What is the delay spread corresponding to a single path? Can someone tell me, if I have a single path, what is the delay spread? If I have a single path, the delay spread is 0. That is correct because I have only one path. Therefore, all the power is arriving only at a single time. Right? So the delay spread is 0. As the spread increases, the delay spread will be greater than 0. Similar to a wired channel. Very good. Exactly. That is exactly correct. It is similar to a wired communication channel. In a wired communication channel, we say we have a single path. Therefore, the delay spread is 0. I'm glad some people are pointing out interesting aspects. Even though I did not point it out, that is exactly correct. In a wired communication system, you have a single path. Also, when you only have a strong line of sight component, you only have a single path. Like in, for instance, distant wireless link. or a satellite link or a basically something kind of a satellite link or a basically microwave kind of a link, you have only a single path. Only in cellular urban kind of environments where there is a dense presence of scatterers do you have multiple reflected or non-line of sight paths. Very good. I'm glad. So there are some interesting questions. I'm glad people are asking interesting questions. I hope people are also able to follow what is being taught. Now this is the last week for these lectures. Also we missed 2 lectures. So this week we are going to have 2 extra lectures on Thursday and Friday. All colleges, please note, I don't know if the message has been sent. On 27th March and 28th March, that is Thursday and Friday, we are going to have 2 extra lectures that we missed. 27th March and 28th March, we will have 2, 8 to 9, same time. Yes, this is including on Wednesday. Yes, our regular Wednesday lecture will also be there. Yeah, everyone understands this. Our regular Wednesday lecture on 8 to 9 will also be there. In addition to this, because we missed 2 lectures on Thursday and Friday also. That is Thursday 27th March and Friday 28th March from 8 to 9 am. Everyone able to follow me? All colleges, please note again, we will have 2 extra lectures on 27th and 28th March, Thursday and Friday from 8 to 9 am. This is in addition to the lecture on Wednesday from 8 to 9 am. Yeah, thank you. Thank you everyone. I'm enjoying teaching this course. Hopefully you are also able to understand, and especially some of the subtle aspects, of the more subtle aspects of wireless communications relating to what is the bit rate, what are the delay spreads and so on. Also, unfortunately, because of the nature of the mode in which this is being taught, and also because of the time limitations, we will not be able to cover advanced concepts such as MIMO FDM. That is purely because of the time limitations. Why? Because normally this course is a 40 lecture course when I teach it at IIT, but here we are only doing 15 or 16 lectures. So for me it is not possible to cover all the concepts in 14 or 15 lectures. So the next time when this course is taught, I will try to increase the number of lectures and cover other aspects also. Alright? Hopefully you understand this is purely because of time limitations, and also because of the distance mode it not able to cover all the concepts in detail. Thank you dear all. Thank you very much. I'm enjoying teaching this course. Thank you.